Hello? 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 Okay. All right. Hello, everyone. My name is Flav Leitner. I work for the network services team. And today I would like to talk about the challenges to provide networking for NFV environments. Just out of my curiosity, how many of you know what NFV is all about? Okay, half I would say. So, okay, good, excellent. I will do some quick introduction, moving from one step to another, trying to introduce the idea, the problems, the challenges. So you will see that I will deep dive in the end into a specific solution. But to get there, I need to introduce some concepts and ideas. So the agenda is concepts and the ideas for the NFV, what NFV is all about, what's the goal, what we want from it. And then we are looking for the requirements. After that, we are going to look quickly about the 10G networks, see what the challenges are there, how it works. Then I'm going to talk about the physical to virtual to physical, the so-called PVP scenario, which is the basic for building the NFV. Then some possible network solutions, especially the ones that we are more used to. They are more commonly available, but there are others. So I'm not covering everything here, all the possible solutions, especially the newest ones. But we can certainly talk about after the talk or even during the Q&A session. Then we'll dive deep into DPDK enable Open vSwitch, because that's the solution we are working mostly with it right now. I will try to explain how it works internally and not go into the bits and bytes, but giving you an overview on how it moves packets around. And then possible improvements that we think it would help to improve the current limitations. These possible improvements, I'm not covering everything possible. Most probably, as you fix one bottleneck, you most probably will find another one. And there are other workaround solutions or solutions that they don't have the same bottlenecks. And there are efforts in upstream to resolve for other solutions as well. But that will give you, I hope that after this talk, you learn the difficulties for virtualizing networks, not only for NFV, but for other use cases as well. Okay, so what is NFV all about? NFV stands for Network Function Virtualization, and what we are trying to do is actually to move from the physical device. You have a firewall. It's usually, this firewall will be a physical device. It has a custom software. It has a custom hardware, usually very specialized hardware, accelerated hardware, so ASICs and so forth, so on. You have load balancer. It's another physical box. You have the routers, or depending on the region you are from, routers. And what we want is we want to have these appliances running inside of a virtual machine. So the step here is actually we are decoupling software and hardware again. The same happened with the other things. SDN, for instance, is decoupling the control plane from the data plane. Here we are decoupling the software and the hardware. And the idea is that running these appliances on a virtual machine, we add this virtualization layer, obviously, running on top of also so-called white box. This is the idea is that it would be a commodity hardware, so nothing is specific. You don't need to match this hardware with the specific appliance you are running it, and you in theory, you should be able to run multiple appliances regardless of the function itself on the same hardware. So that's basically the idea. So what's the goal? Most of you, that's how we operate today. If you want to have a new networking in the company or whatever, you need to buy an equipment. You need to order something. You need to talk with the hardware vendor. You need to negotiate prices. Then you buy something. Maybe they have in stock, or maybe they don't. You have to wait. Then a truck stop by. Someone has to go deploy inside of your data center. Maybe you need more space. So it's a slow process until it gets delivered and up and running. It also has a high cost and less flexibility. By flexibility, I mean you cannot automate most of this process. After that, so assuming that we have succeeded to virtualize these appliances, then you have a fast process, because if you want something, you can just start a virtual machine. It obviously should have lower cost, because most probably you have the hardware already there. You don't need to have someone to come by and wire everything, look for more space, buy more hacks, or you already have a box there that's capable of growing as you need, so you have a spare room. You can just start new VMs. And obviously, with the VMs, you saw some presentations about OpenStack and how easy it is becoming to manage a large number of virtual machines. So we will also need a way to manage these network appliances as well. So if we succeed, if you need something like a load balancer, a router, some firewalls, and etc., you can just click a button, and suddenly your devices will be there. And what are the requirements? Well, in an ideal world, we would like to have this appliance virtualized and don't give up on anything. I mean, we all love performance, right? So, but yeah, this layer here impacts a lot. So it has a cost. And also the hardware is not that heavily optimized ASIC that's running there. So we need to make some, pros and cons here. They might not perform at the same level, but maybe for most use cases, what we have today is good enough. For instance, I was asking if today we have virtualization in some of our products. I asked around, and for some use cases, they really don't care about the performance, because today what is provided is good enough. But for an NFV, let's see. So the challenge for an NFV is that in order to compare with the hardware, we need to go with these two things: low latency and high throughput. How much low latency? I don't know. It depends on the use cases. The market the ones that are driving this effort mostly are telco companies, so they have voice traffic, and voice is usually small packets. Not the smallest one, but small packets, especially for signaling. And they also need high throughput. High throughput means density, right? You can put more customers on the same equipment. If you don't have high throughput, you most probably will have more devices, and then the cost benefit might not be interesting anymore. And when we do these measurements, the requirement is that 0 packet loss. And that really means that 0 packet loss. If one packet is dropped, then the measurement is not valid anymore, and you have to see what is the best number you can get with 0 packet loss. This is the way we saw the vendors, and hardware vendors especially, comparing devices and see, to evaluate which one is best. So we are trying to do the same thing, but in software this time. Okay, let's look about the 10G. 10G is most probably the speed that most data centers are moving or already at it. And it will give you once you understand this, then you can estimate what's going to happen when we move it to 25, 40, or even 100 G. So the worst case scenario that we are going to use is wide speed with the smallest frame. Here's some explanation what the smallest frame looks like. So the Ethernet, we have two pieces mostly. The Ethernet specific, that's not part of the packet, the packet that you are sending, but specific to the Ethernet. This appears in the wide. So 20 bytes for the whole thing, which is 12 for the interframe gap, plus 8 for the MAC preamble. And then the Ethernet frame itself, which is the MAC header, 14 bytes, plus 46 bytes as a payload. The total is 84 bytes. So if you multiply by 8, you convert to bits, and then just divide to 10G, you get this packet height, 14.88 million packets per second. Why this number is important? Because if the software solution can process packets at that speed, it means it reached the line height speed. So we are equivalent to the hardware solution. Okay, so now that we have this traffic height, the peak traffic height, how much time we have to process each packet. So just do a simple math here. We found that is 67 nanoseconds. Well, we know that CPUs are faster, but how much that represents on a software solution running on bare metal. So if you consider a 3 gigahertz CPU, that's about 2000 cycles. So basically we have 2000 cycles to do everything we need with a packet, and that means receiving, processing, and either drop or send someone else. But that's all we got, including if there is any processing, the application that's forwarding, in this case, the appliance. To put also in perspective, one cache miss takes like 32 nanoseconds. And well, this depends on the platform you are looking and the CPU. So if you have something specific, this is just an approximate number, but you can see it's pretty much a half of our budget. So 2 cache misses, we already lost a packet. L2 cache hit is like 10 cycles. L3 cache hit is 36. So in other words, it's a very small budget to deal with this. It's the amount of the cycles you have and the work you need to do, it's really a tight budget. Okay, so going to the software stack. This is the PVP scenario, the physical to virtual and then physical. Traffic generator will send traffic through a physical board, go into the virtual switch or some solution that makes the packet appears magically inside of the virtual machine. Then we have a forwarding solution there, or I don't know, the virtual function, and then back to the traffic generator through another port. This is the basic unit, how we are testing and comparing results with other solutions as well. And this is what I will be using in the next slide as to see what are the weak spots. So basically, that 200 cycle budget needs to cover all this path. All right. Okay, possible solutions. We have a few available today. One is Linux Bridge. Then Open the Switch, SROV, and DPDK enable OVS. Linux Bridge. It uses the kernel data path. It is a good thing because it's integrated with the kernel. So you can most probably use the facilities available in the kernel. But on the other hand, it relies on NAPI and has an unpredictable latency. NAPI means unit. NAPI is, I don't know if you are familiar with, but it's a mix of interrupt mode and pooling mode. So basically, when you start, it's in interrupt mode. and then when the packet comes in, it generates an interruption. This is scheduled. Then a thread will come back and will fetch this packet, but switch to pooling mode. It will pool mode either until a certain budget is reached or there is no more packets. Then it switch back to interrupt mode. So if there are more packets, let's say that you got 64 packets and that's the budget, it will reschedule itself and then continues in pooling mode. As soon as you don't have any more packets, it will go back to interrupt mode. Well, the good thing about NAP is that if you have not at the highest speed possible, you don't spend CPU cycles processing the network card. But on the other hand, it impacts on latency. And we are looking for low latency here. So interrupt mode is really not an option at this point. Another thing is unpredictable latency. One of the reasons is the interrupt mode, and another reasons could be resource allocation. The kernel does a pretty good job with resource allocation, but if we, for instance, get a lock in the way or there is a memory allocation, then our 200 cycles is gone. So we need to have this predictable somehow. And it's not SCDN ready, so Linux Bridge doesn't speak like, for instance, OpenFlow protocol or any other SDN protocol. And if we measure the throughput, very simple test, the phi to phi, so physical to physical. Let me go back a little bit. If this, okay, one. I'm shortcutting here. Physical to physical. Okay, forward. Oops. Physical to physical, I get 1 million packets per core. And that's a very low throughput. So what we can do with the bridge, right? It is used for many other things, and it's very hard to change the way it works or the whole kernel to make it fit in this use case. And another thing to consider is that the QEMU runs in user spaces. So since the Linux bridge is in the kernel space, we need to send, we need some context switches to send the packet through the kernel to QEMU in user space. OpenV switch is pretty much the same thing as Linux bridge. It runs in the kernel data path, also relies on API, unpredictable latency. One good thing is that it is SDN ready, at least it speaks one main protocol. But the throughput, since it leverages the same infrastructure in the kernel, the throughput is pretty much the same, 1 million packets per core. Also, the QEMU is in user space, so there is a solution for that to speed up, which is called vhost, but still it has an additional cost. SROV, I guess most use cases that depend on low latency, high throughput are using this solution. Because with SROV, you can bypass the host. You can literally move the device to inside the guest, expose the device from the host to the guest. So you bypass completely. SROV, it's interesting because one physical port, it appears in the PCI bus as multiple virtual ones. So you don't have only one port, but you might have some up to 256 devices. They are sort of, you don't have access for the whole PCI device. You cannot change, for instance, things that would impact on other devices. So it's quite limited, but still, you have everything you need to send and receive packets. And you can simply bypass the host and moving this device directly to inside of VM. It's not SDN friendly because then you don't have the virtual switch running on the host, so you don't have control. You cannot tell what the guest is doing, or if you want to steer traffic on certain traffic to a certain guest or another traffic to another guest. This is not possible anymore. The devices are physically exposed to the guest. And that's also a problem because there is no abstraction. Then you move, if you do migrations, for instance, you have to make sure the host you are receiving the virtual machine supports the same hardware, the same everything that you had before you need to have on the other server. Although 256 devices, that's a limit that comes from the specification, seems a lot. That's not exactly what the hardware provides today. If you get a card, you might have only 16 supported, maybe 32. I saw some supporting 64 virtual functions. So just because this spec limited on 256 doesn't mean you will get there. So it depends on the hardware also. So good thing about the solution, it offers low latency, it offers high throughput, but on the other hand, you have all these cons, right? Okay, so let's go back to software. One thing that we could use is the data plane development kit, we call DPDK. And DPDK is a set of libraries and drivers designed to, one thing in mind, do fast packet processing, right? So it's an open source project, has a BSD license. There was a talk yesterday from Maxime and Victor. They went a little bit deeper on what is DPDK. So, and their talk are pretty much related to this one as well. So I would recommend to watch their talk to see what they're doing in the vhost virtual land. So what's the usage of DPDK? Receive and send packets within a minimal number of CPU cycles. That's what we are looking for. But what DPDK is not, and I'm putting this here because quite a lot of people confuse that, is not a networking stack. So it doesn't replace the Linux kernel. If your application needs a socket, for instance, you won't get the socket here. There is no TCP processing. There is no TCP congestion control algorithm. It just gets the packet, deal with the buffers, deal with rings, and send out a packet on the device. Okay, TPDK pull mode drivers. So TPDK has these pull mode drivers, and what is that? Is a way for you to get packets from a network card directly in user space. So the buffers are all mapped in user space. The NICs, thanks to the VFIO interface, we can simply get packets there or send packets out on the network card very quickly. Okay, so now speaking about Open vSwitch plus DPDK. Open vSwitch has a kernel module. You probably saw that if you already played with the Open vSwitch, you saw that there is a module there. There is also a module in the Open vSwitch repository. But the kernel part of it is just a cache. So the user space does all the intelligence. The user space does all the processing. For instance, a packet comes in, you match on it, and then you accumulate all the actions you need to do. And once you have this big, giant rule that says I need to match on all these fields and do all these actions, this is pushed to the kernel. So when the next packet comes in, the kernel knows what to do. But to get to that point, user space did all the processing. All the processing. Well, DPDK provides libraries. Those libraries, they work like pre-allocated memory. They use huge pages. It's busy pooling, no interrupts. You have lockless rings. You have rings with a single producer, multiple consumers, or single consumers and single producer. So we can use these libraries and the driver to have the vSwitch doing all the work, and that's what we are doing, DPDK enable Open vSwitch. So remember the 14.8 million packets per second. If you measure physical to physical, we can get around 16 million packets per second. So that's a huge bump. There is one trick here that it's not, the processing is not done per packet. One of the features that the DPDK brings us is batching. So we are moving batches of packets. But still, if you put on the traffic generator and measure, you will get around 60 million packets per second per core. But that's not for free. We need one core, 100% busy running the PMD thread. Okay, let's look about OVS DPDK for NFV. We need to provide network connectivity to virtual machines. QEMU runs in user space. But now we have DPDK, we have OVS, everything is running in user space. So there is this interface called vhost user. It is a shared memory between QEMU and the virtual switch. So we can simply copy packets on this ring, and it will appear on the guest. So no kernel at all in the host side. The throughput's about 3.5 million packets per second per core. Default features enable in the PvP scenario. The system is not heavily tuned. But since this is very CPU bound, and it depends very much on the platform you have, the CPU you have. So if you have a high-end system, most probably you get a better number than I have here. We also support multiple streams, multiple queues, which means if you enable more cores to process more queues, this scale up quite linearly. So I would say with 4 cores, we can get line 8 speed, even pushing to the virtual machine. But yeah, this system needs to be carefully tuned. We'll talk more about that in the next slides. How does it work? Basically, we have this pull mode driver thread. It wants a CPU, and that means nothing else should be running on that CPU. If you have something interrupting the CPU, you are pretty much stealing CPU cycles from it, and we already know that the budget is very tight. So any interruptions, any scheduling events, or anything that happens there, a locking, a memory allocation, something like this, it doesn't work. So DPDK provides us all the resources pre-allocated. We already are working in busy pulling mode, but still we need to make sure that this thread wants the CPU. The devices can be distributed between the PMD threads. I say the device here, but it's actually queues. By default, the device provides one queue, but you can enable more queues, and then distribute these queues to different PMD threads. Each PMD thread will busy loop and busy loop for packets, and then do the processing. And the model there is run to completion, which means once the thread gets the packet, it will go through the whole processing until either the packet is sent out on another port or drop it. So we don't have any scheduling in the middle. And one thing that I already mentioned, one of the tricks to virtually expand our our budget for processing is to have batching. So you move, instead of packet by packet, you move like 20, 32, or 64 packets at a time. OK, so let's do an X-ray of the PMD thread to see how it works. It's quite simple, but due to simplicity, sometimes you have some consequence of it. So basically, you have any ports. In this case, it's a generic scenario. You can have any ports as you want. You have the queue is represented by this box. So this is the receiving queue, which this box here represents the PMD thread. It will pull for packets for each receiving queue. Once it gets the receiving queue, it will push the batch to the forwarding data plane. That's the vSwitch. It will do all the processing with the packet. Let's say modify the destination IP address, remove a VLAN tag or add a VLAN tag, anything you can do in the SDN network. And then either will drop the packet or send out on a TX queue for another device. That's basically how it works for for any use case you want to use the PMD thread. As you can see, as you add more ports or queues, this actually could be any queues from the same device, but it's the same thing. So as you add more queues, you will spend more cycles here pulling each port, and one impacts on another, of course. OK, so going back to just to fit things together, you know better what I'm talking about. We discussed this to simulate the NFV. So here I have, a firewall running where you can, use Juno OS, log in on Juno OS or something here to establish that. And here you have 2 logical ports, the vSwitch in the middle, 2 physical ports. This is represented here. So you have 2 physical ports here and the 2 logical ports, and this weird arrow simulate to represent the forwarding. So just to show you the equivalence of what I am talking about. I represent, as you can see, this physical port, it sends traffic to the virtual switch, but it doesn't send traffic out to the traffic generator, so I didn't connect the TX QE here. So you only have the RX when it's relevant and TX when it's relevant. We'll talk more about the second picture, but this is just to put things into places. Okay, this is now with a more realistic scenario for NFV. Let's talk about the packet flow. So this is the physical port that receives from the traffic generator. It's called number 10. It will come here. The thread will pull for that. We'll match this data plane rule, open flow rule. It says, oh, coming from port 10, send out on port 21, goes to the RX of the 21, appears in the guest. The guest does the forward to the TX QE inside of the guest, which becomes the RX QE outside of the guest. And then the packet goes back to the pooling. Then it's sent out on the forward data plane. It will see another rule here. Oh, packets coming from port 20, send out on the port 11, and then it's sent out here on the TX QE and back to the traffic generator. So one thing to note here, the packet goes twice through the PMD thread. So remember that budget we actually have to divide by 2 because of this. Okay, how to measure throughput with 0 packet loss? What we expect is that we have a setup on the traffic generator at constant height. Then the system is constantly dropping packets. We decrease the traffic rate and repeat until we find something that works out. Okay, that's actually, it happens. We should look where the packets are being dropped because there are the bottlenecks we should improve. So in this case, there are 3 red stars, the 3 weak spots where we should look more in the detail. The first weak spot is the receive QE for the physical device. What happens that? Basically, if the PMD thread is busy doing something else and it's not pulling this device fast enough, this QE will overflow. And it's a physical device, so it has a limited number of resources, and some network cards allow you to extend a little bit, but still it is limited. So it's a classical producer-consumer problem. If this is not fast enough, pulling packets out of this device, the queue will overflow and you will drop packets. So it's really important that this runs fast. The other thing is this receive queue here. For the same problem, if this is not running fast enough, this queue will start to build up, and at some point it will overflow. The difference between this and the previous one is that the drops are reported in the port stats. So you look at the device, you see the drops you can identify. In this case, you don't see the drops stats in the host, you see the drops stats in the side of the guest, because when the application is trying to push packets to this port, the port is full, so it's dropped inside of the guest, and it's not visible in the host. Then the other weak point is the TX QE here on the vhost user. But that's not a fault in the PMD anymore. What's happening is that the guest is not running fast enough. So the guest is not fetching packets, is not pulling packets from this virtual device. And that so the PMD is trying to push more packets, but there is no space, so what we can do? There were, again, the same producer-consumer problem. So as you can see, it's like a clock, right? So if something goes off a little bit, there will be consequences, and depending on what's off, one of these 3 points will blow up. Okay, measure throughput with 0 packet loss. I told you about this, but in reality, I saw this happening. System is stable for a period of time. You can see traffic is running just fine. You go out to lunch, and then you come back. You have like 2 packets dropped. Very low throughput, and the goal is to understand the drops. Here's, we saw the 10 gigabit budget. I put the table here with less, because that's what the virtual machines are doing anyway. So this is the budget for the 3 million, 4 million, 5, and 6. Just calling attention for this number because it will appear later, but basically that's what we are looking at to see how significant are the impacts of others. Remember, packets go twice to the PMD, so the real budget for packet processing is this one. All right, I measured how much time I spend pulling each device and how much time I spend processing the device. So physical device for processing, I spend 3.1 microseconds, and the user egress device, which is coming back from the virtual machine, I spend 2.1 microseconds. Others are really low. Processing here is 0 because we are not using that. And the pooling is quite fast. So these are the main ones. But the total, if you sum up all the numbers, you will get 6.2 microseconds to loop a packet, a batch of packets between in and out. All right, batch. So we saw the number is 6.2 microseconds is 24 times more the per package budget I showed you before. That happens because of batching. So we are virtually extend our budget doing batching. So batching is a fundamental thing. Assuming that we would have like a perfect batch of 32 packets, we could have 5 million packets per second instead of 3.5. So something is happening. Trying to estimate the numbers with the 3.5, 0 packet loss, the budget will be this. We can calculate or estimate the batch size to 21 in average. This is something maybe we can improve, but it depends on other things, right? If you go there and take out all the packets you have at that moment, but it's not 32, should we wait for more? It might introduce latency. So what is wasting time? Internal resources? Yes, external resources. Internal resources, if you look at how it works, there is no locking, memory is pre-allocated, there is no reason for it to stop. So it runs 100% of CPU busy. But we should look at the external sources of problems. What they are, how much significant they are. We look at the budgets, we know the time we have, so we have a way to tell if they are significant or not. For instance, RSU callbacks. This is inside of the kernel. So just to remind, BMD processing budget is for 3 million packets per second is this value. I use this cool tool called ftrace. It shows you the functions that are called in the kernel for a specific CPU. You can filter that. And then it has a nice timestamp. And you can calculate how much it takes to run the kernel RSU callback. And this is the number I got without the preemption cost. I mean, moving from the PMD thread back to the kernel, run everything, run the CPU callback, and then back to the user space. 50 microseconds. That's roughly 8 batches. One solution for that, disable the RSU callbacks on a specific CPU list. And no CBE pool also. But we need to do that, otherwise there is no way to get rid of this. Okay, next slide. Another thing is time interrupt. There is a periodic time interrupt that also causes scheduling issues and task accounting. We can use this parameter here to move to a no hertz. Reduces a lot the time interrupt, but doesn't solve the problem. There still will be 1 interrupt per second. That's unfortunate. I know that there is a patch being worked in upstream to get rid of it, but at this point I couldn't have tried yet, so I don't know if we could do that. Okay, other sources of problems, scheduling issues. We have to take out the hierarchy balance because any hardware interrupt on that CPU running PMD thread can impact. We have to use ISO CPUs, which means take the CPUs out of the scheduler. We don't want any tasks running on that CPU. We had to disable Watchdog. Watchdog will periodically check something that has some impact as well. Power management, and that depends on your platform. You can try to use this to limit the state of the CPU to the maximum. So at least you are sure that your CPU are running at a certain level. Hyper-threading, depending on what is running on the other thread, it can also impact in terms of cache trashing and false sharing and so forth and so on. So this is important to look at, either disable or know what you're running. And real-time kernel. Real-time kernel for other stuff, because as you saw, if the guest is not running fast enough, so we need to take care of the QEMU threads as well, especially the ones running the vCPU there. Real-time kernel helps to make sure the kernel will not introduce a high latency there. Okay, possible improvements. You saw that it cycles between the devices. So if one device is not working or is lower, it affects others. One possible solution for this is using the DPDK all-thread subsystem, which is kind of a scheduler of threads in user space, highly optimized, but it adds a cost. So our budget for line height speed is 200 cycles. Does that worth it? Maybe our devices are good enough. It depends on the case. For most hardware that I tried, the impact, the old OVS, when pushing packets to a virtual machine, if there was no space in the ring, it would retry for 100 microseconds. Yeah, 100 microseconds is really too much. Then we change it for trying again. If it succeeds, try send more packets. If it succeeds, try again up to 8 times. It's a lot better, but still, you waste time doing that. Should we just drop the packet? Then we are not with the 0 packet loss. Should we try again? Then we lose time. So there is a compromise there. vhost user has a feature called measurable buffers, which is buffer injection to support buffers above the M2. If you disable that, you pretty much simplify how it works so it runs faster. This is changing. As I mentioned, there was another talk yesterday. They did some nice work here. Increase the batch size, but again, we saw the average was about 21. There were some tests in the past that show it 32 as a good number. Above that, it doesn't work quite well. Below that, it's not that efficient. So this is something we could look more as other things change. Increase the virtual ring size. This is being done in upstream. BIOS settings, this is very, very, very important. Each hardware vendor has some features there. Some are not really clear if they are related or not. So we had to talk with our hardware vendor to see the best possible options. If you look at the DPDK side, there will be some chips there on what to enable, especially on Intel platforms. One obviously way out is the faster platforms and CPUs, right? And one thing that we need to do more is to improve the CPU isolation. And this is how to make the PMD thread really wants the CPU and not having any interruption. OK, questions? Maybe I went too fast, but I can scroll back the slides.
What about the latency? Is there some disadvantage of the batching?
Well, we are trying to push as many packets as possible with very small packets. So if we can get, there is no queuing or very small queues. What do we measure the latency? It's not what the hardware can provide to you, but it's the question was regarding to latency, if I have numbers to show about that. We are still looking at, there are measurements about that, but due to other facts like packet drops, we think that first we need to get rid of them to rise the throughput, and then we'll talk more about latency. But so far, latency, the other team that measured that told us that this is not a problem yet. Yes?
In your setup, you use the 2 ports for receive and 2 ports for transmit, right? And used inside.
OK, this one. Yes?
And so we have 2
Yes.
Did you try to use two CPU and with different poll drivers for every received queue?
Okay, so the question is if I try to use multiple PMD threads, kind of having this better distribution. So I could improve this by adding more PMD threads. Yes, we tried that. Basically, you can do two things. Either you have more PMD threads and then you distribute the ports, or you can increase the number of queues and then distribute the queues. For instance, you could have 4 PMD threads, and for each of it processing one queue from the same device. So the host user would provide you 4 queues, and the traffic would split equally between them. It helps to improve it pretty much scales linearly. So as you add more PMD threads, you have more power to process traffic. But on the other hand, you have one more busy core that you cannot push it to idle, for instance.
But you mentioned that you had to disable the hyperthreading, right?
Yeah.
Did you try to place both of these PMD threads on this, to switch on the hyperthreading and put both threads on the same CPU and to see the cache locality with the same core?
Yes. So the question is, if I try to put the 2 PMD threads on the siblings running on the same core. So basically, we would leverage the fact that those two were running on the same core and they could share caches. It helps for some use cases, but might not help in the other use cases. Since it's a forwarding data plane here, and depending on the actions you are executing, you might have some cache trashing in the middle. So in this case, my data plane programming were just 2 rules, so it most probably would help. But in a real world scenario, we need to try that. Yeah. Yes.
You mentioned that Intel has some capabilities to hardware to support the DPD key. Could you name them?
I told Nick, you mean for the network card?
Yeah.
Because right now DPD.
No, for the DPD key, I don't know, probably some functions or.
Okay. So the question is if I could name some of the Intel features that allows DPDK to work. Yeah. Okay. So DPDK started as an Intel project, and in the beginning it was limited to Intel cards. But right now we have other vendors, so most cards, at least the most common ones, are supported. And the feature is pretty basic. It depends on the other feature, which is called VFIO, or UIO if you don't care less about security. But the common network cards you can use, yeah. Yes?
Yeah, you mentioned some performance numbers, and you mentioned just the frequency of the processor you used to get these numbers and to measure it. What kind of hardware more specifically have you used for these benchmarks? I mean, was it just like normal box I can buy at the store, or was it some kind of HP?
It was a good server, but not a high-end one. This is a Xeon. I don't remember exactly the models we bought. Haswell? No, it's not Haswell. Mine is a bit older than that. So see, it's not even Haswell. Yeah, most probably Ivy Bridge, yeah.
Yeah. And the second question, all of these numbers seems very impressive, but okay, what kind of configuration do I have to use for kernel for system so that I can use this together with virtual machines? How do I isolate this from the impact of the virtual machines? Is there some research or some recommendation?
Yes, basically you have to, the PMD threads needs to be isolated. The question was if I have to, what can I do, or if there is any recommendation to isolate these threads from other things. Yes, there are documents in the DPDK, for instance, and there is a guide inside of the Open vSwitch project, install-dpdk, and there is no, it's not, it changed. So it's DPDK, and there is a DPDK advanced guide. This advanced guide will give you good tips to how to get there. We try to keep it updated because we also want other people to look into this and help us to improve the performance. Yeah, and for the QEMU, libvirt has support for CPU pinning. So you can tell where the vCPUs will be running, the threads that handles the vCPU will be handling, and then you can isolate those threads in the same way you would do for the PMD, but for the QEMU. The problem is that QEMU also, at some point, will need to do syscalls and other stuff, so that's why I mentioned in the kernel with RT real-time support. Make sure that it doesn't get stuck with a locking, for instance.
And by kernel, with real-time support, you mean just some package I can have from Red Hat, or some self-compiled kernel with tunings or hacks?
Red Hat does provide the RT kernel. You need to talk with our organization to see how to get that. It's not. I don't think it's part of the standard RHEL. Yeah, I'm sure that's not part of RHEL. But you can get that package from the upstream. I'm not sure. I'm not looking into that, but I believe the patches are public and you can compile yourself.
Okay,
I guess there is this guy here that knows about
Our real-time offer is based on PrintRT. The kernel with PrintRT patch set. That's the real-time kernel. With a lot of tunings in it, but you can get it upstream.
Okay, so.
Thanks.
Yes?
Yes, the possible improvement, have you considered using cache allocation technology so that we can reserve S3 cache lines to the OVS process?
That's on our to-do list. I haven't tried yet, but it's something we should look at, yes. Yes? Oh, sorry, I forgot to repeat the question. If we look at into cache allocation technology for improving this.
I asked about scalability because if it must be into one CPU and you have many virtual machines, you want to fire out more and more virtual machines, you will have to manually modify tune kernels just to fire out more virtual machines.
Yeah, you will have to look at your system and say how many VMs you want to run and isolate them. You can pre-isolate them and let the CPUs available. So when you start the VMs, the CPU will be there. But I agree with you. It's something that it's not really easy to isolate everything right now. That's one of my last bullet was to help improving the kernel isolation, at least for that CPU. Okay, I run out of time, but I will be in the highways if you need more. Thank you. Sorry about that. Oh, VJ?
Yeah, VGA.